Hello and welcome back to Dr. Logic Awkwardly Does Logic. Today you're going to get the second lemma in the completeness proof for S5 that we've been working our way towards. And this is a really easy lemma and really kind of magical when you see how the proof works, because this is where the constructiveness comes in. As I've been saying all along, what makes this particular completeness proof special is that it gives you a method for generating the counterexample when you've got something that's not a theorem. But even cooler, it gives you a way of generating the proof for every single thing that is a theorem. So let me get up the whiteboard so that I can state the theorem, or rather the lemma, because it's this lemma and the previous one that go together to make the whole theorem. The lemma is, if phi is in ordered modal conjunctive normal form and it passes the test, then it is provable in S5. Very simple lemma, really simple proof. So let's see how this goes. It's going to work our way through essentially what it means for something to have passed the test. So what we're going to do is essentially give a procedure that for every conjunct that passes the test generates a proof of that conjunct in S5. And then there will be kind of bits and pieces that go along the ways to stitch everything together so that you've got one proof instead of many different little proofs, but those are just details. They don't really matter so much. So let phi be in ordered modal conjunctive normal form, and let ci be a conjunct of phi that passes the test. And remember, if it passes the test, then every conjunct in this formula will pass the test. But we're just going to start with one. So if you've got a finite number of conjuncts, we can start with the first one and then the second one and so on. But I'm just going to take an arbitrary one for now. Because we know that CI passes the test, we know that one of the following is valid. So either it's going to be beta or delta. Remember, beta is the purely propositional part disjoined to the propositional part of the possibility claim. Or it's going to be gamma 1 or delta, that is valid, or all the way up to gamma n or delta, depending on how many necessity claims that we have. One of these is going to be valid, and all of them are purely propositional. So you know what this means? They're a propositional tautology. This means we can write it down as the starting point of our proof. So we've got two cases here. Either we've got that it's beta or delta that is, so we'll call this case 1. Either it's beta or delta that is the one that is valid, or it is one of the gamma I or deltas that is valid. It'll be a slightly different proof in each case, but it's just the two cases because it's going to be one or the other. These are the only ways for the thing to pass the test. So suppose that it's beta or delta that is valid. We then prove this conjunct CI as follows. First line of the proof, write down your propositional tautology, propositional logic. Then we have a theorem from T, which you remember says that if P is true, then possibly P is true. This is just the converse of the T axiom, the contrapositive of the T axiom, necessary P implies P. So we'll take a substitution instance of this, namely that if delta is true, then possibly delta. So this is a T theorem with uniform substitution, substituting delta in for P. Now, propositional logic tells us that if we have P or Q and Q implies R, then all of this together gets us that either P or R is the case. So this is a propositional tautology. We could write it down in the proof. We could do some substitution. We could do some modus ponens. But remember, even though it's been a long time, these are the sorts of propositional maneuverings that we just sort of shove into the background and we don't pay any attention. What really matters is that we have beta or delta. And from delta, you can get possibly delta, which means that with some propositional reasoning, we actually have beta or possibly delta. So this is some propositional logic twiddling on lines 1 and 2. We also know that if we have P, then we also have P or Q. This here is another propositional tautology. And however many disjuncts that you want to add, or of whatever complexity, and you don't have to add them on the right, you can add them on the left. Again, propositional details that we don't really care about. What we care about is that we can stick in as many of these gammas as we want, and in some cases it might be none. Wait, that isn't even what we want. We're going to do something even cooler than just sticking in all of the gammas. We are going to stick in all of the necessity gammas. So there we go, all the way up to necessarily gamma n or possibly delta. This is, again, just propositional logic reasoning. We're adding disjuncts to a disjunct that we already know is valid. And now you see exactly what we have. This is the conjunct that we are trying to prove. Now, let me get a clean whiteboard for the second case. So suppose that our conjunct CI is of the form gamma I or delta. So one of these, where gamma in the original conjunct has a box in front of it, one of these is the tautology. So, suppose that I can actually write down the thing that I need to be writing down. What we want to suppose is that it is something of the form gamma I or delta in conjunct I that is valid. Now, again, same reasoning, because it is valid and it is purely propositional, we can write it down. It is one of our axioms. Now, the rule of necessitation says if you've got something that you know, if you've got some line written down, you can stick a box on the front of it. So now we've got necessary gamma I or delta. Now, think back to one of our K axioms, which says that necessary P or Q is equivalent to necessary P or possibly Q. Take a substitution instance, and what you get is necessary gamma I or possibly delta. So this is a K theorem with uniform substitution. We are substituting gamma I in for P and delta in for Q. And this is the theorem that we're using, plus, some modus ponens, etc. And now we can do exactly the same trick that we did on the previous case, which is all of the other disjuncts that we need to add. So gamma 1 or up to, we've already got our gamma I, but we might have other things going up to gamma n or possibly delta. Here, I'll put my annotation here. This is, again, just propositional logic, adding all of our extra disjuncts in. And now we have our conjunct CI. Now, this isn't the end of your proof, but it's functionally the end of your proof. What you would then need to do is convert this essentially do this for each of the conjuncts. So here is, say, conjunct 1, and then you take the proof that you generated for the second conjunct and you put it on there. And then if you've got more conjuncts, and then you need to do a line in the proof that says we can put all of these conjuncts together. This is going to be propositional reasoning. And then you want to essentially unwind all of your conversion into modal conjunctive normal form, ordered modal conjunctive normal form, reduction to first degree, etc., until you get back to your original formula. As I said, this is all just little stitching up bits. It's stuff that we've already shown before that you can do, but that's it. The basic thing are these 4 steps. You find out which one is the tautology, you write it down as your first step, and then either you use a T-theorem to stick a diamond on the delta and then do a little bit of propositional reasoning, or you use necessitation plus this theorem from K to get your box onto the gamma and then a diamond onto the delta, and then everything else is exactly the same. So this is super cool. And if I can find the stop share, I can convince you that this is super cool. It also means that the proof of our next theorem, the main theorem that we're trying to show, is going to be really easy. I promise you, next video, gonna be great. After that, we will actually see the entire process from start to finish. I will give you an arbitrary formula, and we will go all the way through all of these different bits to determine, is it a theorem? Is it not? If it isn't, give a counterexample. If it is, we'll give a proof, and it will all come together, and everything that we have been doing will be so worth it. Anyway, join me then. Until then, take care. Cheers.